Section 9.3 is all about the similar right triangles. So our lesson objectives are to identify similar triangles, solve real-life problems involving similar triangles, and use the geometric means. Our essential question: how are altitudes and geometric means of right triangles related? So let's get a couple vocabulary words in our notes. First, arithmetic mean is the average of two numbers. We're very familiar with the arithmetic mean. You do this whenever you are averaging your grades. Geometric mean is a little bit different. It's a number x between two positive numbers a and b that satisfy the following relationship. So here we see a proportion. So geometric mean, you will always set up a proportion in order to solve. You would do your cross products like we've always done since last unit. So you have your x times x, you have your a times b. And a couple of vocabulary words that are a review is these values, the x's, are the means. They're always the same number. Again, they were always the same number. Your extremes can be different numbers, and that's these position values. So your cross product is x squared equals a times b, and then to solve for x, you've got to square root both sides, which is how we end up with x by itself equal to the square root of the product of a and b. All right, let's find the geometric mean of 12 and 27. First, start by placing the 12 and the 27 in the a and the b position, and then x in the other positions. So your 12 goes here, 27 goes here, and then your x, same variable in the other two positions. Your cross products would result in x squared equals 12 times 27. 12 times 27 is 324. Then you would square root both sides, looking to undo the radical. And since 324 is a perfect square, x equals 18. All right, let's find the geometric mean of 18 and 54. Now, since geometric mean ultimately results in the square root of the product of these two values, it's possible for you to skip the cross multiplication and get straight to that step of x equals the square root of a times b. So we end up with the square root of 18 times 54, which is the square root of 972, which is not perfect. So we need to start a list of factors of the value that's not perfect under the radical until we find the largest perfect square. You always start with 1 in itself. So 1 times 972, then go to consecutive values after that. So 2 in this case times 486, and then we get to 3 times 324. We just learned in the previous example that 324 is a perfect square. So there's where we can stop. So you end up with the combination of 324 and 3 under the radical, separated into two separate radicals. So you get square root of 324 times the square root of 3. And square root of 324 is a perfect square, which results in 18 square root of 3 for our value of x. So our geometric mean of 18 and 54 is 18 square root of 3. On page 482, it states that in a right triangle, the altitude from the right angle to the hypotenuse, so that's from here to here, divides the hypotenuse into two segments. Our two segments are here and here, creating relationships between the legs, the altitude, hypotenuse, and two hypotenuse segments. This leads us into the right triangle similarity theorem. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So if you were to sketch the two smaller triangles after you have sketched in your altitude of the original. You've got these two smaller triangles. If you were to separate them and sketch them separately, you could see that all three triangles, so the original ABC, are similar to the two smaller ones. And here's our similarity statements. So let's just practice identifying similar triangles. So use this diagram and write similarity statements. So let's start by sketching the triangles separately. Here we have all three triangles from smallest to largest. So triangle TSU, triangle RTU, and triangle RST. Our corresponding angles are in the same orientation, and so are the sides, making it a lot easier to write our similarity statement. So triangle TSU is similar to triangle RTU, which is similar to triangle RST. Remember, order of the letters matter. Alright, so let's take a look at this roof that has a cross-section that is a right triangle. The diagram shows the approximate dimensions of this cross-section. Let's find the height, h, of the roof. Alright, first step is to sketch all of the triangles separately and label and have them all going in the same orientation. Next, this allows you to set up your proportion between the similar figures. We know that we can use YW, that's what we're trying to figure out, which is the height, so that must be in your proportion. And YW compares to ZY, which is equal to XY. So YW and XY are in the same position, so they're in the same spots within the proportion. And then compared to ZY, which we know the value is 5.5 and corresponds to XZ, which is 6.3. So you want to use all numbers and one variable. Then do your cross product, so the height comes out to be approximately 2.7. Alright, so let's revisit one of our core concepts, which is the geometric mean. Once again, two positive numbers a and b is the positive number x that satisfies the proportion a divided by x equals x divided by b. So when we cross multiply, x squared equals a times b, and we square root both sides, which means x is equal to the square root of a times b. So pause the video here and look back at your previous examples and see if you can figure out the geometric mean of 24 and 48. Alright, let's see how you did. Did you get geometric mean of 24 and 48 is 24 square root of 2. Completely simplify your radicals at all times. If you type it in the calculator, it should come out to 33.9, approximately. Alright, so the geometric mean leads us to the geometric mean altitude theorem. And it states that in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. I mentioned this earlier, but our two segments are C, labeled C in this picture, and labeled D in this picture. These are the two segments that are highlighted. For simplicity, we'll call it piece of hypotenuse 1 and piece of hypotenuse 2. So piece of hypotenuse 1, piece of hypotenuse 2. And here's what we know about these pieces. The length of the altitude is the geometric mean of the lengths of the two segments of the hypotenuse. So here's how your proportion would look. Piece of hypotenuse 1, in other words C, divided by your altitude, in this case E, is equal to the altitude, which is E, divided by piece of hypotenuse 2. So our two segments that the altitude divides the hypotenuse into are the extremes, and the altitude is our means. Then we also have the geometric mean of the leg theorem. And it states in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. So again, it's C and D. But this time, the length of each leg of the original right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. So if we were to simplify this entire theorem, we could simplify it to this proportion with these simple words. Your whole hypotenuse divided by the leg equals the leg divided by adjacent piece of hypotenuse. So let's start by considering leg A. If we're to look and use leg A, then our proportion would look like this. Remember, the whole hypotenuse, so in this case labeled F, divided by the leg we are using as the means. So in this case it would be leg A, so right over here. And it's the original right triangle that we're looking at for identifying our legs, equals the leg, so the same, divided by C. And that's because C, this little section right here, is the adjacent part of the hypotenuse to the leg that we're identifying. And then if we use leg B, again, proportion starts with the whole hypotenuse length, in this case labeled F, divided by the leg you're considering, which in this case is leg B, so it's the longer leg of the original right triangle, equal to that same leg divided by just the small piece of the hypotenuse that's immediately adjacent to the leg you're considering. Alright, so let's consider all of our theorems for finding the values of w, x, y, and z. So let's start by finding the value of x, because it's probably the simplest and doesn't require a theorem. X is the segment that our altitude divides our hypotenuse into, so we know one part of our hypotenuse is 3, and we know that the whole hypotenuse is 9, so we can simply subtract 3 from 9 to get x. So the result is x equals 6. So now let's take a look at finding the remainder of our values. So let's go to w next. So we'll set up our proportion. We'll use our leg theorem because it's a leg of the original right triangle. So we would say 9, which is the whole hypotenuse, divided by w, which is the leg we are identifying to solve for, equals w divided by 6. We just figured that out from our work here of subtracting 3 from 9. So it's the small piece of the hypotenuse that's immediately adjacent. So do your cross products, resulting in w squared equals 54. Square root 54, which simplifies to 3 square root of 6. Alright, let's next figure out another length. So the other leg, y, so set up your proportion. 9, the whole hypotenuse, divided by y, which is the leg we're trying to identify next, equals y, the same leg, divided by 3, the piece of the hypotenuse that's adjacent to the leg we're identifying. Do your cross products, resulting in y squared equals 27. 27 is not perfect, so you'll need to simplify to 9 and 3. Square root of 9 times square root of 3. Square root of 9 simplifies to 3, and then square root of 3 is not perfect, so you've got 3 square root of 3 as the length of y. Alright, next we'll use the altitude theorem. Set up your proportion. In this case, we've got 6 and 3 that we're trying to find the geometric mean of, and z is the altitude. So 6 divided by z equals z divided by 3. Do your cross products, you get z squared equals 18. 18 is not perfect, so find two factors. The largest perfect square would be 9, factor of 18. So 9 and 2, you get square root of 9 times the square root of 2. Square root of 9 becomes 3. Square root of 2 is not perfect, so your final answer, z, is equal to 3 square root of 2. Alright, now you try this one all by yourself. Find x, y, and z using the two theorems, the leg theorem, geometric leg theorem, and the geometric mean altitude theorem. And we'll check our answers in class. And that's all. See you soon.